Hi everybody, welcome back. So in this course we have gone through all the methods to get help, get yourself unstuck. We've gone through all these methods to get data into Python from all these different sources, JSONs, APIs, web scraping, databases, and we've gone through all these different methods to clean data, to get it ready to be analyzed, including SQL and in-depth into pandas. After all of that, we're finally ready to get into the data and start to see what's there. So, exploratory data analysis. It's the last part of the class. For this module, we're going to be working with tabular methods. Methods of exploring a data frame that are displayed as tables in your Python environment. Next module, we're going to start working with visualizations. We're going to do static visualizations. Then we're going to wrap up with interactive visualizations. But right now, tabular methods. So first, let's talk about the whole notion of exploratory data analysis. The phrase exploratory data analysis, or EDA, comes from a statistician, John Tukey, who is considered one of the originators of data science. Really cool guy. You should look up his work and his biography. He described exploratory data analysis as an attitude and a flexibility. So it unlike other kinds of analysis, it's not so set in stone what this thing is and what it can do. He says that the goal of EDA is not to answer a specific research question, but rather to dig into the data and get a better sense of what the important properties of the data happen to be. So it's very self-guided. You kind of feel things out. You'll see what this means through various examples today. So EDA includes fast and simple approaches to collect some preliminary findings, to look at the assumptions that are underlying other methods, see if things are distributed normally, and then identify problems, complications such as missing data, such as outliers and stuff like that. So there's no fixed set of methods that comprise EDA. So Tukey phrased it like this. He said, "No catalog of techniques can convey a willingness to look for what can be seen, whether or not anticipated. Yet this is at the heart of exploratory data analysis. The picture-examining eye is the best finder we have of the wholly unanticipated." So he sees this great value in just looking at the data and seeing what's there, right? And that's what we're going to do. We're going to use tables and graphs just to see what's there. Now, I want to note that this part of the data pipeline should be a very joyful part. So if you're feeling this whole data thing, if you enjoy it, then everything that we've just been through, the data wrangling, it can feel like a puzzle. You know, like you have to take things, you have to put them in the right order. It's like a puzzle box, and then finally you have the puzzle assembled. You've got a clean data frame. At that point, you can dig into it. Like if you have a puzzle box, you open it up finally after all the work and you see what's inside. We're at that stage. We are having assembled the clean data set. Now we're digging into it to see what's there. Hopefully you have some excitement. You've got some joy at this stage. Okay, so the first method for exploratory data analysis is to look at descriptive statistics. There's a few broad categories of descriptive statistics. First, there's measures of location, which are also called measures of central tendency. And these describe the values that what you might think of as a typical data point can take on. So it could be the mean, it could be a weighted mean, it could be the median, things like that. Now there are measures of variability or dispersion, and those report the typical distance that each data point is away from its mean or middle. And so we could think of the variance and the standard deviation in this category. There's also the interquartile range, which we'll define in a bit, the minimum and maximum, and percentiles. And then measures of frequency, how many times each distinct value appears. So for a category, it's just the count of every category for a continuously valued feature, then you could take those continuous values and put them into bins and then count how big each bin is. And so this category includes the raw counts. It also includes percentages. So these are the three big categories of descriptive statistics, and we'll go through them now. So first, for a measure of location, we have the mean. And so here I have the mean of the Joe Biden feeling thermometer from the American National Election Study. And so we have, on a scale from 0 to 100, a mean of 42. That is, individuals who were surveyed in the American National Election Study were asked to rate Joe Biden and a number of other politicians on a scale from 0, meaning the most unfavorable, to 100, the most favorable. And the average is 42. Now, we might be concerned with outliers. So that becomes more important for a feature like income, in which there are going to be some values at the top that are many orders of magnitude bigger than other values. So if we're concerned with outliers, we can always compute a trimmed mean. We can use the SciPy stats module and use this function trim mean. When I write 0.1 here, like right here, it means that I'm calculating the mean after removing the top and bottom 10% of values. So when I do that, the mean doesn't change very much. It goes down to 41.5. Another way to account for these outliers is to calculate the median. So with the median, it's the 50th percentile. It's the value for which half of the values exist above and half of the values exist below this value. So that's the median. Now, for a variety of reasons, we might have a survey that uses sample weights, or there might be other kinds of data that uses other kinds of weights. Sample weights are used when a randomly drawn sample differs demographically from the general population. And so we use these sample weights to make our random sample more in line with the population. So we can use those sample weights to calculate things like means to get a more accurate picture. So just as an example, let's say that we're trying to do a survey of the United States, of the adult population of the United States. 50% men, 50% women. But for whatever reason, the sample that we get is 60% men, 40% women. Well, we could reweight each row for a man's responses down because they're overrepresented, and we can weight the rows for women up because they're underrepresented. So, okay, if we have weights as a feature in our data, then we could use the NP average function. So the average function from the NumPy package with the weights parameter. And so you can see right here that I'm going to take the average of the Biden thermometer with this column, the weights from the A&ES function. Okay, this is after removing the missing values on Biden. Okay, so that's a way to remove the rows with missing values for the Biden thermometer because the NumPy function doesn't know what to do with missing values. Anyway, when we reweight it, then the average goes up. It was 42 before, now it's 43. Okay, if we wanted to take a weighted median, then what we have to use is the W-quantiles package. It's a separate package. And then we could use the weighted.median function from that package, and then it gives us the weighted median, 47 in this case. Okay, now, measures of variability report on how far from the mean the typical value in the column happens to be. There's a discussion of this in the notebook, but we'll just get right into the statistics here. So for the variance, for the standard deviation, we've got the var and STD methods. Okay, so here we have the variance and the standard deviation here in a list. For the minimum and maximum, we have min and we have max. And so for Biden, it goes from 0 to 100, no surprise. Percentiles are the values in the column for which a specified percent of the values are below that value. So if we're talking about the 30th percentile, then the 30th percentile is equal to a value for which 30% of the rows are less than that value. A quantile is the same as a percentile, but we use proportions instead of percents. So the 30th percentile is the 0.3 quantile. So we can get quantiles with the quantile function. And then, so it's a method applied to a particular column, and then the quantile method, and then a list of the quantiles we want. So here, 0 is the min, 1 is the maximum, 0.5 is the median, and then I've got the 10th, 25th, 33rd, 67th, 75th, and 90th percentiles for the Biden thermometer. And they're all right here. So when we say 67th, 2/3 of the rows have a Biden thermometer of 60 or less. Okay, now percentiles are cool because they can show us the degree of variability in that column. So the closer those percentiles are together, the less variability we have. And one quick and easy way to measure that degree of variability is with the interquartile range. So what we do is we figure out the 75th percentile and the 25th percentile and then take the difference. So for Biden, here's the 75th percentile, it's 70. So that means 3/4 of the rows have a thermometer score for Biden of 70 or lower. And then the 25th, 7 or lower. And then the difference, 63. Okay, so that's a pretty quick and easy way to understand the variability. The bigger the interquartile range, the bigger the difference between the 75th and 25th, and so the bigger the spread there. Okay, let's talk about categorical features. They can either be ordered or unordered. An ordered categorical feature has categories that can be put into a natural order. So here are, in the ANES, the responses to the feature that asked, how do you feel about a universal basic income? And so people were asked to rate their position from oppose a great deal all the way up to favor a great deal. So what I did was I replaced these values with numbers, and then I treated it as a numeric feature. Once I treat it as a numeric feature, then I can use these descriptives again. So on this 1 to 7 scale, the mean is 3.5, the median is 4, okay? And then the standard deviation and interquartile range. So I can understand these if I think about universal basic income on this 1 to 7 scale. Now, whether or not the categories are ordered, we can always generate a frequency table. And so here are the counts for the universal basic income. We've got 1,007 people in the data who oppose it a great deal. We have 377 who favor it a great deal. We've got all of these values here. So value counts gives you the basic frequencies, but we can do better. There's a package called side table, and side table has a method called freq, F-R-E-Q for frequency, and it gives the same information, the same counts, but it also gives the proportion, the cumulative count, and the cumulative percent. Now, cumulative only matters if these are in order, but they're ordered from most frequent to least. So, still, it's prettier information and more information than we get from value counts. Okay, we can also turn a continuous valued feature like the Biden thermometer into categories with PD cut. So if we write PD cut, give it the feature, and then write 10, it's going to give us 10 equally spaced bins, right? Each one of these comprises a range of 10 on the thermometer scale. Or we could pass it a list, and we could write the cutoffs ourselves. We write minus 0.1 because we want something less than the minimum value, right? So that this one from minus 0.1 to 0 This is just all the zeros. There are 265 people who rated Biden 0. Okay, and then these are all the 100s, 95 people who rated Biden 100. Okay, and here's the last and coolest thing I want to show you with descriptive statistics. There's a package called Pandas Profiling, and it provides this function profile report that gives you an HTML interactive dashboard right there in your Jupyter Notebook, and it shows all these great descriptive statistics for all of them. There are examples in the notebook. Please play around with it. It is so cool.